So I'm going to talk about the basic sciences and its relation to the advanced technologies. As you know now, science is a journey. It's not a journey of a single person, but it's a journey of humankind. And well, in my personal story, let's say, I started doing science in my master's degree by solving some differential equations related to the general relativity. I'm a physicist. I have done my PhD in particle physics. During my PhD, I moved on the experiment. I worked at the CERN Large Hadron Collider on the hadronic calorimeter. And then afterwards, I started to move on to the little bit more on the technology part. That means developing detectors for high energy physics. And now I'm working at the biomedical department at the Yıldız Technical University. So it's a journey, as you see, within 25 years, you see we go from basic science to the advanced technologies, even in a person's lifetime. So today and yesterday, you heard a lot about the basic science, or why we are talking about development in science. Well, it started with simple questions like, when will be the next storm coming? Or when will be the next drought coming? So when should we plant our seeds to get our food for the next year? Or these are basically related to the survival, right? The fear of nature. But also, when we look at nature, even up above the sky or around us, we saw strange things like colors. Well, the rainbow, it has particular pattern. It has a kind of color scheme that goes from one light or one color to another color. So why is so? Why insects or flowers, why do they have color? Do insects see colors so that they go to particular flowers for food? What are the patterns that we see in nature, like this animal fur? Or even in some plants, there are some patterns. So questions, fear, curiosity that brought us today, the science that we know today. So when you type nature in Google and translate it or find the meaning of the nature, it is from ancient word physis. So as you know, again, science in the early days or in the ancient history has been known as the natural philosophy of nature, right? So as a physicist, I can probably say no one can shoot me, but we think that physics is the mother of all science today. So the chemistry, biology, they all stem from physics. So physics is the branch of science that deals with the structure of the matters, the interaction with the matter, within the matter, let's say, among the matters, and try to understand the fundamental constituents of the universe or observable universe. Of course, science requires methodology. So only looking is not enough. We have to create some methods to see the nature, to see the universe. Looking versus seeing is very different things. Maybe by looking you could be a great writer, right? Or you can write maybe beautiful poems. But to become a scientist, you should be able to see beyond what is shown to you. So from the beginning, humankind is learning and thinking and asking questions. And this brings us today, the science of today. But once again, the seeing is, as I said, is different than looking. So when you look at the first, let's say, the baby steps of the science, you can see that Aristotle gave us this idea. When he observed an object, after giving an initial push, he saw that this object slows down and eventually stops. So according to him then, the natural state of an object is always to be at rest. And this has been kept like this for many centuries and no one questioned it. So for any object, the natural state was to be at rest. But later on, I mean later, when you look at the difference between the dates, more than 1,000 years later, some guy created, or let's say used another approach, assumption. So he said, well, if the friction is eliminated, this is an assumption. Maybe in his days there was no way of eliminating the friction. Of course there was maybe ice, so the friction somehow maybe was seen between the touch of two objects to each other, and using ice could eliminate the friction. Maybe this was his starting idea, we don't know. But he said if the friction is eliminated, objects always move continuously without stopping. So you see, it is contradictory from the previous statement. So according to Galilei, now that the natural state of an object is either to be at rest or to go with the same velocity or same speed to forever. So this is a huge change in paradigm. So the first thing we should keep in mind that there's an assumption based on observation and also a kind of huge jump in the thinking of experimentation, because one should go then find a place where there's no friction between the two objects and repeatedly do the experiment and see that the Galileo was right. So, of course, as you saw in these two sentences, the science is trying to find answers in the simplest terms, try to come up with the laws of the nature with very simple statements. So today when we look at the laws of nature, we see that, well, they rely on small number of concepts. There is one or two equations explaining that concept. And there are certain assumptions around that formulation, and they can, most of the time, alter our view of the nature, and sometimes they can revolutionize how we look at the world. So this is a really huge extra, how should I say, I'm maybe making huge assumptions here, but when you see this formula, F is equal to m times A, many of you have seen this formula before, one can say simply that this led to the industrial revolution. So knowing the force, knowing the acceleration, the mass, the mechanics, the thermodynamics, and so on, all coming from the classical understanding of physics or classical understanding of our nature, led us to the industrial revolution. When then we understood the energy and the mass, or the relation between them, with this simple formula, on the left-hand side we have the energy, on the right-hand side is the mass and the speed of light. So this can be also used to explain how we were able to invent our nuclear age, because the energy can be created from mass, or mass can be gained from the energy. And you see here another formula. This is rather maybe cryptic to some. Anyone can tell me what are these indices? Have you seen such kind of mathematical notation before? Mu, nu, right? This is a tensor equation. It's a form of, let's say, differential equation. But you can say that this is regarding, or this is using 3 coordinates and also the time coordinates. So this is written in a tensor form that we have here 3 space coordinates and 1 time coordinate. So in fact, this is maybe a bunch of equations written in a single line. But this is the famous equation that gave us the general relativity of Einstein. So you can also see this here on the left-hand side. I'm not going to give you a lecture on general relativity, but this left-hand side is about the geometry of the universe, or the geometry that is created by the mass of cosmological objects. And on the right-hand side, you see this, the G is the constant, universal constant G, and you see the energy and the momentum, or energy and the mass on the right-hand side. So this led us new things, or think about new things on the cosmological scale. So I'm going to give you today a few examples. Maybe this is the first time you see this formula, but we use this formula in everyday life to go from one place to another place. I'm going to show you one example. So as I said, the method of science is observation and experimentation. And by using the observation and the experimentation, we try to understand the natural events. And we try to come up with invention of a theory. Sometimes the invention of a theory can also predict a certain observation that we should make when we look for it. So for example, when you have some discrepancy in the cosmological data, or let's say orbital motion of a planet, you can predict that maybe another planet is causing that orbital change of that planet. And you can predict that maybe there is some another cosmological object over there somewhere which we don't see, but the mathematical calculations or your theory predicts that there should be another object somewhere there. So it can lead to new discoveries, or by doing some observations, you can find another object in some place else in the universe. This has been done many times in the history. And from that, from the observation and experimentation, you get the knowledge, and you have the progress of the mankind, progress of the society, or as we have seen today and yesterday, progress of technology. So, when you look at the history of the physics, now today we have an understanding of our nature governed by 4 forces. These are the gravitational force, the electromagnetic force, weak and strong nuclear forces. And many of you, I'm sure most of you know about, okay. All right, so the gravity, or the gravitational force, is between 2 objects that carry mass, and almost every object except the light that I will talk about has mass. So the interaction between them is called the gravitational attraction. It is only an attractive force, and it is the force between the objects in the universe, the force that now you are able to sit in your seats today and listening to me. The electromagnetic force is the force that keeps the atom intact. You see the electrons are orbiting around the nucleus. The electrons carry negative charge. The nucleus, or nuclei in plural, has the positive charge, and the electrons are able to move in the orbit of the nuclei. So the molecular bindings, the surface attraction between the objects and so on, the friction that we have talked about, are all electromagnetic forces. The weak nuclear force is the reason why we are able to get the solar energy. So the burning of sun is due to the weak force, the radioactive decay, or transformation of neutron to proton or proton to neutron. These are all happening inside the nuclei, and the weak force is responsible of those changes. The strong nuclear force is a force which keeps the protons and neutrons together inside nuclei. So if you think about it, the protons, they have the positive charge, and in order to keep them in this small, tight space inside the atom, there has to be another force, because the positive charges, they repel each other. But since they are inside the nuclei in a very tiny space, there has to be another force. there is also a particle which is called a neutron, which doesn't have any charge. But anyhow, somehow this structure is kept together, and strong force is responsible for that, let's say, binding of the nuclei. And inside nuclei, we have the proton and neutron. These are the constituents of the nuclei. And even within them, there are other particles called quarks or gluons. So all these kind of interactions and particles are the subject of physics, and we use them to understand the nature. But we need, as you saw, we need to have some understanding about the dimension. Because when we go from cosmological scales to the subatomic scale, we switch from 10 to the minus 20, 19 meters to 10 to the 28 meters. You see there's about 10 to the 40 in terms of dimension, or in terms of the distance, 10 to the 40 power difference. So the human size is about a meter, right? Our cell is about 10 to, one cell is about 10 to the minus 6 meters. The atom has about 10 to the minus 10 meter radius. The proton or neutron have about 10 to the 15 meter radius. And even, let's say, the smallest scale that we can think of today, or we can make calculations today, is about 10 to the minus 19 meters. And the farther point that was observed, I think this was observed by Hubble telescope, is 10 to the 28 meters. Maybe there's a recent observation that I don't know of. But you see the difference, 10 to the 28 minus 10 to the minus 19, so 10 to the 40 meters almost difference between the scales. So doing science means having technology to do this kind of scale change, going from 10 to the 15 meters to 10 to the 28 meters. That means we have to use technology to be able to do the experiments and observations required to do these things. So when we look at the nature, we need to use devices. You see, they are all looking to something, right? Either by a small telescope or a large telescope or a space telescope to see the places or to see the dimensions close to the 10 to the 28 meters. Or we are using optical microscope or electron microscopes to see 10 to the minus, let's say, 10, 11, or 12 meters. Or we are using particles, which I am going to also mention today, to see inside the matter or inside the nuclei, which is 10 to the minus 15 meters. So light cannot go that deep. We need to change our view or change our techniques to be able to see inside an atom. So, as I said, curiosity is bringing us today here. And this is the Mars rover Curiosity. And even this little robotic device can tell us the importance of science and technology working together. So this is the landing scheme of this Curiosity robot on Mars. You see the stages of the landing procedures depicted here in this figure. And at each stage, there's tremendous of calculations, simulations that has been done before doing this mission. And you see, so for example, what kind of, how much fuel we will need, what kind of motion that our object will encounter during this landing procedure. So at what altitude we should deploy our parachute, and what will be the heat, and what kind of materials we should use to deflect this heat, and so on and so forth. So tremendous amount of engineering, technology, and science met here in order to succeed in this project. So most of the present day technologies, we can safely say that coming from basic sciences. So it is not an exaggeration to say today's science is tomorrow's technology. But we should also keep in mind that basic science should be part of our technological advancements. And even today, we need to have a place for advanced technologies to grow. solar cells. We heard about solar cells. Maybe you heard them, you know, from the let's say from the primary school, but still we don't see solar cells around us replacing the fossil fuels, right? So we are still in process of developing better, more efficient, cheap solar cells. So that's why still it is in the bed of basic science, or it's in the domain of basic science. So people are still trying to come up with better materials to do high efficient solar cells. Maybe someday they will really replace many of the other means of energy producing, but not today. Tremendous of development has been done. Many people are still working on at the university research laboratories, at the companies in the, during the R&D phases and so on, but they still need a basic science background to do this kind of R&D work. So it's not easy to put a line between science and technology. Many speakers talked about this, but there are a few distinct things about science and technology, or the approach that they take. About finding or searching knowledge about nature, if you really try to summarize what science is. But technology is the process of applying knowledge. And one is driven by the curiosity. Let's forget about fears, because we don't fear nature anymore. We are about to destroy it anyhow, right? Unfortunately. So science is about nature. The technology is mostly driven by our needs, either by human need or society, the needs of the society, right? Science uses methods of asking questions, finding answers, making generalizations and predictions. However, technology employs methods of synthesis, finding solution to needs. So if you think about it in this simple way, think about yourself as a baby. You played two games. Either you destroyed your toy by keeping or taking it apart, or you build things like putting things as a Lego game. Right? This is like science and technology. Science tries to take things apart, look at the constituents of the things, like the matter, like the universe, but technology tries to put things together to make something useful out of knowledge. So science is evidence-based, objective observation, and it tries critical analysis, and it needs repetition. It doesn't matter if you did the experiment in your lab and you said that, well, I did the quantum teleportation, so I was able to put this cat from this place of the room and brought it here by doing the quantum teleportation, and you wrote an article about it. I don't care if I cannot repeat it by following the exact steps that you have taken in your laboratory. So I have to be able, or anybody, anywhere in the earth, on the earth, or in the universe, doesn't matter, because the laws of nature are universal. So anybody in any place in the universe should be able to repeat that experiment at under the same conditions. But technology doesn't care about that. It's a process-based. It thinks about usefulness. It thinks about the cost. It thinks about the mass production. Right? So the view on the final product, let's say if a observational prediction is the final product of science, or the final product of any technological thing, they are two different things. Engineering, as you have seen also today, is a kind of bridge between the technology and science. So society, do you think that society needs science? Maybe on the surface you don't think that society needs science, but when you look at the advances of any society, even at the, let's say, art level, can benefit from advancements in science, like painting maybe. When you understand color better, you can create new forms of art. And understanding color means maybe knowing a little bit about the electromagnetic waves, or how you can create a different pattern by using sound waves, for example, and so on. I mean, if you know a little bit about science, you can do a better artist, maybe during your art sessions. And also, as I said, technology is the outcome of the science, so therefore, at the second order, society get benefit from science also. The way of life or the way we live in this era by using our phones, by using our cars, we are trying to get rid of the difficulty of driving by inventing self-driven cars, right, and so on. So we all need something from science. So therefore, society pays for science, right? So maybe knowingly, maybe not knowingly, we are also, as a member of this society, we are also paying science to do research, technology. It answers our needs. So as I said, the engineers are the bridge between them. But when you look around, you see these things. Maybe many of these things are now the technology of 80s or 90s, right? They're even become older technologies. But when you look at them, you don't see science. So when you use your cell phone, you don't think about Maxwell. When you use your GPS device, or even today we don't use any GPS device, we have our cell phones that has GPS chips inside. We don't think about special relativity or general relativity or the solar flares that are impacting on the satellites. So the forces that we have seen today affecting on a satellite on the orbit, we don't think about these things. But we should really know about, a little bit about the science behind these technologies. So these are the famous 4 Maxwell equations, the electric field and the magnetic field. And you kept hearing today, electromagnetic waves travel with the speed of light. But do you think why, or do you know why? Or if you be careful about hearing what I say, the electromagnetic waves travel at the speed of light. I'm telling something about electromagnetic waves and also telling about something light. Are they the same? No? Okay. Some say yes, some say no. Who says they are the same? I didn't say anything about particle yet, right? I said electromagnetic wave and light. I said electromagnetic waves travel at the speed of light. And I ask why. Light is visible, okay, one hint. Are the light themselves, right? So the light is a special term that I will talk, is something we use that term or that word light for the visible portion of the electromagnetic spectrum. Light is some small portion of the large or wide electromagnetic spectrum. It was Maxwell, when he thought about the change in the electric field or change in the magnetic field, could create one another. And this change, going from magnetic field to electric field, or from electric field to magnetic field. Did I say the same? I don't know. So change in between happens with the speed which is equal to 3 times 10 to the 8 meter per second, which is the speed of light. This only happens in the free space. If there's nothing on space, that change can happen between E and B. So the electromagnetic field, for some reason, can change to magnetic field, electric field, magnetic field. So the way it changes is different. There are some different patterns about this change, but the speed of change is equal to c. And he was able to do the calculations, and he was able to combine the electricity and magnetism. So this is, again, another paradigm change. When we, up to that time, maybe people were thinking electricity and magnetism as 2 different things, but from that day on, now we think about the electricity and magnetism are the same things. Only the important thing to keep in mind, if there's a time relation, that means if with respect to time, electricity is changing to magnetism, that means there's the electromagnetic wave. Einstein, let's talk about the GPS. So he thought about the special relativity. Even today, many of us cannot comprehend what it means, or general relativity. So that means the relative motion of objects, if objects are in relative motion with respect to each other, and if the velocities of the motion are comparable with the speed of light. That means if you are moving with a speed close to the speed of light, things get a little bit weird. Time that you measure and the person who measures the time who is on motion could be different. The distances or the length of a person who is standing that he measures and a person who measures the length during the motion could be different. So these are all subject of the special relativity. And also the general relativity. Up to that time, we were thinking about the gravitational force between the two objects as like m1 times m2 divided by the square of the distance between them. So that is like action at a distance. There's nothing in between these two objects, but somehow there's a force which is inversely proportional with the square of the distance and so on. But Einstein imagined the universe as a a flat surface. When you have an object sitting on that surface, it can create a kind of sink in that surface. That means it can bend the space and time. An object moving around that object, a secondary object moving around that object, is doing so not because of the gravitational force in terms of, let's say, Newtonian or classical physics, but because the space-time is now curved. The space and time is not flat in the general relativity. There's a curvature that is caused by the massive object. So what does it mean? Well, think about the GPS devices now. Let me go to this slide. So at any given time, you have about 10 to 20 satellites orbiting around the Earth at the altitude of like 20,000 kilometers with the speed of 14,000 kilometers per second. And our phones now looking at 4 to 5 different satellites and receiving time signals from that satellites. The resolution, I think 14,000 kilometers per second or so, because they travel twice around Earth. So it's like they travel on the orbit in half a day. I might be wrong about that number. I will check that. But so 1, 2, 3, yeah. So let's say here is the location, and we are receiving time signals from these 4 different satellites. They send us the time information with a resolution of, let's say, 10 nanoseconds. But due to the motion of these satellites with respect to Earth, and due to the curvature difference, here on Earth, we have more curvature when compared to this location. Let's say this is the location of satellite. The curvature is here less compared to the curvature on the surface. So the clocks, let's say digital, even the digital clocks, they tick different on the satellites. Due to the special relativity, there's a time difference about, I think, 7 microseconds. And due to the general relativity, there's a time also difference between the clocks on Earth and the clocks on the satellite, about 45 microseconds. So in total, there's about, one is ticking faster, one is ticking slower. There's about 35 microsecond difference between the clocks on the satellites and the clock on Earth. So we need to have a nanosecond resolution in order to have a meter scale resolution on Earth about our location. So how this should be done? So one way of thinking that, well, how about making these clocks ticking a little bit slower or faster with respect to time? Or how about designing clocks that tick slower than the clocks that tick on Earth? Right? This is now an engineering question, and people with very good ideas about designing clocks for satellites that take into account this time difference, so that we can have precise, let's say meter or half a meter precise location based on GPS satellites. So as you see, even this, let's say, innocent looking equations, they have to be taken into account when designing a GPS positioning system. So today we cannot think of a life without internet. And maybe you heard this before, www, the internet, was discovered at CERN for physicists to do their communication. So this was a laboratory-wide communication protocol that was developed or invented for people doing work at CERN, but later on it became open and society started to use it. And many of us cannot think of a day without internet. We became addicted to internet today. The antimatter, right? Antimatter was discovered as, let's say during cosmic showers, or let's say during the atmospheric experiments. First particle that was discovered, antimatter, is the positron, the antimatter of the electron. And today we use antimatter for medical purposes. So PET, or positron emission tomography, is using antimatter to the medical imaging. So all things coming from basic science are now helping today to have better, healthy lives. So when you Google today, what are the emerging technologies, you can come up with different infographics, 10, 20, 50 emerging technologies that were created by different companies, different societies, and so on. This is just one of them, top 50 emerging technologies. They have many things in common. For example, energy is the hot topic today, sustainable energy, right? Nanotechnology, where is it? The sensors and instrumentation, like LiDARs, the graphene sensors, microelectronics, medical devices and imaging, 5G, 6G materials, storage, energy storage by using the hydrogen cells, or by using new generation lithium-ion batteries, and so on. So all these top emerging technologies, top 50, top 10, whatever, every year they change, but depending on who prepares them. But if you think about it, it really boils down to the development in the last 100 or 150 years. So think about it, humankind, at least, that we see the records of, goes back to the BC 10,000, right? Maybe a million years back, but when we see the first records of the history, it starts from the 10,000 BC. All things that we see today are based on the development of the last 100 or 150 years. So, therefore, we should really think about the history of the atom, which is really, really, as you will see today, intertwined with the advanced technology. So I'm not going to bore you with the atomic models of the 18th century or 19th century, but let's focus on the modern view of the atom. Before Schrödinger, or before the 926, the atom was taught classically. So there's a certain positive charge at the center. Negatively charged particles called electrons are orbiting around that nuclei. So this is the classic view of atom, right? This is the classic view of atom. However, today in modern science, we think atom in a very different way. So here is the picture, I mean drawing, not a real picture, but here's a picture of the atom. We see the positively charged nuclei here at the center, and a cloud of negative charge around it. So we no longer think electrons orbiting around well-defined orbits around the nuclei, but they move in a certain probability clouds. What does it mean? Well, starting from Schrödinger, we think about the atoms in a different physical view. So we think about it in terms of quantum physics. We no longer think with certainty about location, the measurements, and so on, but we think about them as wave functions. So when we think about the location of the electron, when we think about the energy of the electron, we have to do calculations based on this equation, which is Schrödinger's equation. There's no time component here, but this is a differential equation. Like, you can think of this as the F is equal to ma, but now called Schrödinger's equation for atom, for hydrogen atom. So the psi is the wave function, which depends on the space and time, x, y, z, and t. There's the Planck's constant, this is another universal constant, and there's the potential, this is the force between nuclei and the electrons orbiting the nuclei. So, yes. So when you try to solve this equation for the hydrogen atom, you come up with that kind of solution. So you see that there are regions where you find the electrons spending their time the most, and it changes when you go higher and higher energies. So you see from the solution of the Schrödinger's equation, you get 4 quantum numbers. All right? So like n, which is related to the energy, L, which is related to the orbital, let's say, orbital information or the shapes of the orbit, and then S, let's say S, also about the energy on the shells, and the final quantum number about the spin of the electrons. The electrons, they carry something called spin, which gives about their information or orientation when you put them inside the magnetic field, up or down. This is the solution for the hydrogen atom, but when you start putting more protons and more electrons around them, you come up with solutions, and in the end, you can come up with a table which is composed of the 4 quantum numbers, N, L, M, and so on, and then you can arrange all the atoms that you have observed in nature based on those quantum numbers. So this is the footprint of the chemistry, right? This is the periodic table of atoms. So that's why I said, as a physicist, I can safely say that chemistry is coming from physics, right? Of course, in order to understand chemistry, you cannot solve the Schrödinger's equation to get the chemical properties of the atoms or elements here in this part of the periodic table. You have to use different tools to understand the bonding or binding of the different elements with each other, the color, the taste, and all the chemical properties are kind of collective properties of the atoms when they put together. But their fundamentals are based on the quantum mechanics, quantum physics. This, as you see here, is like 1800s, 1900s. We discovered many, many new elements. We filled up the periodic table. Even there were some predictions about new elements, because when you put them together, you saw that there's a spot empty. There's no element in nature that has been discovered yet. So people were able to predict that, well, there has to be an element with such and such numbers, with such and such properties, and then later they were found. Right, so the classification helped us to make some predictions and the observations later on. But that view wasn't enough to build new technology. So let's talk about single atom, a couple of atoms together, or 10 to the 23 atoms together, 1 mole of material, right? So think about it. So when you have the atom, let's say the silicon atom, you have the energy levels. These are the quantum numbers that I have talked about coming from the solution of the Schrödinger's equation. And you are able to put electrons based on their spin states on these energy levels. Have you taken any chemistry class before? Organic chemistry, right? So you know the game of putting the electrons in the orbits, right? So this is good for one atom. Well, when you have the same type but a second atom, so you put the energy level here. Now you cannot put them on top of each other. It has to be shifted a little bit. And then you put the electrons of the second atom here, and so on and so on. So if you have 3, 4, 5, or so on, if you have a molecule, let's say like here, if you have 10 to the 23 same atoms, you are not able to distinguish the energy levels anymore. You have to talk about energy bands, right? So believe me, if you can count, there are 10 to the 23 lines here, if anyone wants to count. So this energy band of solids paved a way to understand different properties of the materials. Like we are able to categorize materials like insulators, semiconductors, conductors, based on the energy band theory. So, for example, at 0 Kelvin, all the electrons are here in the valence band. And the electrons can go to higher energy levels if they have energy greater than 4 electron volts. And there's this gap between the valence band and this conduction band. So it is difficult for electrons to jump from this band to that band. So that kind of materials are insulators. But also we have materials, it is at the room temperature, it is very easy for the electrons go to the conduction band. That means they can move freely. And we call this type of materials conductors. So there's no gap between the band, which is filled with fully filled with the electrons, and the conduction band, which can have electrons coming from the valence band. But there are some kind of materials, either in between insulators or conductors, and we call them semiconductors. So the band gap between the valence band and the conduction band is less than 2 electron volts. Let's say 0.8 electron volt, 1 electron volt, and so on. So this view, the band theory of materials, helped us to understand more. So how about if we produce impurities? So instead of having the same atom everywhere in the crystal, how about if we put materials, or let's say impurities, like silicon atoms here, but we have the phosphorus here, or silicon atoms, but boron here. So that kind of impurities that we have observed give us devices like diodes. So I'm going to speed up a little bit. Give us diodes or transistors. So when you put materials with impurities together, like negative electron, the materials with the electrons, or materials with the holes, you can come up with transistors, or you can create devices putting all these transistors or other passive elements like resistors and capacitors together. So even in the small size, this is 2 times 3 millimeter squared an operational amplifier. So this is, you see, the picture of the device itself. So it has maybe hundreds of transistors. And you can think of today's computers or the CPUs that you see i9th family. They have billions of transistors. And they work like the binary state of the transistors, because these transistors can act like ones and zeros as the binary, right? So you have the TTL, transistor to transistor level, 5 volts. So if your voltage levels is below the 1/3 of this VCC, it's 0. If it is higher than 2/3 of that voltage level, it's called 1. So you can have this devices making calculations or processing, doing processing based on the combination of zeros and ones. So you see the scale is very small. And in today's CPUs, as I said, there are billions of transistors. So we are running out of space. So we need to invent new, right? Quantum computers or quantum computation is the new emerging, let's say, technology of today, but it is still in the baby steps. You may think of the quantum computers today like the vacuum tubes before the transistors. I'm afraid I will not have time to go through all these things, but as I said, the light is electromagnetic wave. So only the small portion that we see here, we call it light, but in general, electromagnetic light, or electromagnetic wave, sorry, is a radiation, and we use radiation or light sources to see things, right? So this is an advanced technology that we see today. So this is an X-ray image that Röntgen took of his wife, and this is an X-ray image that was taken about 5 years ago. This is a 3-dimensional X-ray image, still using electromagnetic waves, right? Electromagnetic radiation, but the technology has changed to come up with this 3-dimensional X-rays. So today we are using free electron lasers. That means we are producing laser light by using the electrons, by accelerating the electrons, and we have the X-ray flashes in the end, and we use these X-rays to study molecules, to study cells. The biological studies can be done by using these X-rays today. So let me finish up. But we are limited with the light. So we cannot use light to see smaller and smaller. We have to come up with a better idea to see something smaller. So we need to change our light to particles, because as you said, there's a duality. Every particle can behave like a wave. Every wave can behave like a particle at certain circumstances. So quantum mechanics tells us. And by accelerating, by circulating these particles, we can smash them together. That means we can use particles and see inside materials that no light can go, let's say, at the nuclei level. So I'm going to stop. I have a few slides more, but if you have questions, maybe I can answer them by flashing through those slides. Thank you very much.